All right, thank you, Mano. It's great to be back. This is our first. This is our actually second time doing the guest workshop. It has been a great experience working with like both Atrium and also Uniswap Foundation on various front. For kind of launching some cool hooks. So I'm Mo. Just a quick introduction about me myself. I have been in the blockchain space for more than 6 years. Initially started as more of a research role and working and collaborating with a bunch of people on Ethereum Foundation and working on state channel and layer 2 scaling technology over the years. Me and my co-founders, Junda here is also online, have built one of the biggest cross-chain interoperability protocol called Stellar. Some of you, if you came from like the DeFi era, probably used the Stellar C bridge. And more recently, we started to build a new project for 1.5 years now called Brevis, which is something that has some very strong and interesting synergy with the Uniswap hook design, and in general any modular kind of DeFi design that is in the next generation evolution of DeFi architecture. So I'm very glad that I have this opportunity to talk to you guys and also share about how you can build some very interesting hooks, using data-driven insights. Powered by Brevis and ZK technology. So, just to share my screen here, let me just take one. Is my, Mano, not sure if I have the permission to do this. Let me try this.
Yeah. You should be able to do that now.
All right. Okay. This works. Yeah.
Yep.
Awesome. So yeah, well, great talk to you guys. So for this guest workshop, there are two parts. One is the first one is that I'm gonna do an overview introduction of what Brevis does, and of course I will kind of introduce this more pertaining to the context of the Uniswap hooks, and then Junda, who's our CTO here, will actually provide a deep dive into the documentation we have and walk through some very concrete examples how you can build hooks with Brevis. So without further ado, Brevis, what we're trying to do is that it allows you to actually bring data-driven dApps with a smart ZK coprocessor. Like what Brevis is a ZK coprocessor. What do we mean by ZK coprocessor and why it can actually introduce this type of new design pattern to dApps? Well, before we actually kind of dive into that, I just want to pull up an analogy here. If we look at the web architecture before 2000, in the entire web, the entire internet is actually built on this type of synchronous architecture. So you have this monolithic web server that does everything. Like, every user comes, it does have request handling, does access control, do the computation, data access, everything, and return the result to the user. So it was very clear back then, as the user of internet scales rapidly, this type of architecture won't actually hold water. So, this is why we have quickly in the last 20 years evolved into this very modern web architecture based on asynchronous design, where the web server itself is a very thin layer of software and the kind of infrastructure that is essentially just a coordinator. So all of these different users will send like high concurrency requests to the web server, itself, and the web server will turn around and send individual and kind of essentially distribute these specialized requests as asynchronous calls to these specialized backend services. After these specialized backend services like AI, do big data analysis, authentication, after all these services do their job, and the callbacks will be sent to the web server, and the web server will assemble all these results, coming back from the callback function calls and send it to the user and give user a holistic and unified representation of the user experience. So this is like how every single major Web 2 application works today. Like Facebook works like this, Twitter works like this, Google's very famous GFE architecture works like this. So this is how Web 2 evolved like in the last 20 years. But if we look at Web3 today or blockchain application today, we're in a stage actually worse than the Web 2 before 2000. So everything is synchronized for sure, because like we treat the entire web and smart contract platform or EVMs or blockchain VMs as this as this kind of a monolithic server. But the worst thing is that it's actually having worse performance as a single server because how blockchain works, as we all know, is based on a distributed consensus protocol. So there is like actually replicated compute, replicated storage, based on, running on top of a huge communication overhead incurred by the consensus protocol. So, this architecture, we also all know on scale, even with layer 2s, it is still based on a very kind of a, high overhead consensus protocol underlying. So just to kind of use a very, very simple example to illustrate this, right? So, on centralized exchanges today, many of you probably use Binance, Coinbase, and stuff like that. So they all have this type of trading volume-based fee discount or trading volume-based fee schedule, where if you trade at different level of trading volume on monthly basis, your trading fee in the next month will actually reduce and reflect your kind of a VIP level for the exchange. Right, so this exists in every centralized exchange. There's no exception. But if we look at all the DEXs, Uniswap included, there's no such function available. Why is that? Well, turns out that because it is actually very, very expensive on blockchain to actually directly access historical data on chain, historical transactions and historical states and historical events about user swap behavior directly on chain, because that involves like kind of you need to do a lot of very, very expensive Merkle proof to prove a certain transaction actually is included in a historical block header, and you need to kind of trace that block header to the most recent header. So these type of computations is just too hard to do on blockchain, even though they sound actually pretty simple if you think about it in the off-chain setting. Many of the off-chain kind of solutions, indexing solution does this computing every day. But if you want to do this on-chain, it is impossible, right? So if you want to calculate what is the trading volume, very, very simple. What is the trading volume for a user who traded 10,000 trades in the last 30 days on Uniswap? And you want to give it give him like 50% trading fee discount. Well, you cannot do that on chain. If you want to do this on chain, it costs you 40K in transaction fee and 8 hours of processing time. The core reason, again, is there's no trust-free access and computation capability on these historical on-chain data, like events, like transactions, like storage states, which are essentially variable values. So, what Brevis introduced here is, we have a full documentation describing how, and blog post describing how a underlying works, is that it introduced the asynchronous architecture to Web3, where we treat the blockchain as essentially a very, very thin layer of software that still handles asset-related computing, and it will be a central point to coordinate these off-chain computing resources. So basically, it will be able to allow, it will be able to kind of offload many of these kind of complex and data-heavy computation to an off-chain environment. But the immediate question you might ask is that, okay, so if you offload these transactions or computation to an off-chain environment, how can you ensure that the security and trust-freeness of the blockchain is actually maintained end-to-end after the computation is done and after the result comes back to the blockchain, right? So this is where we actually use ZK technology to essentially generate the proof of the computation itself, but also about the proof and attestation about the input data, right? So if you want to do some computation based on some transaction, historical transaction or historical events, we Brevis generate two things, as a ZK proof. One is that the transaction inputs actually are valid, like these transactions actually happened in the history of blockchain. And then whatever the computation you want to run on top of it is actually correct, like the result is correct. And then these proof and also the computation result will be posted back to the blockchain and back to the smart contract, where the verifying process, the verifying of the proof is actually a very, very light computation compared to the computation to actually do the full computation process. And then, after the blockchain can verify the computation the result can be used in the smart contract directly without violating any trust assumption of the blockchain itself. So there's, even though that you send your computation task off chain, there's no additional trust assumption involved and introduced in the process. So this is like the magic of ZK coprocessor here. So, Brevis is a full off-chain computing stack, encapsulating ZK coprocessor, ZK VM, and ZK ML. But, the most relevant thing we want to talk about today is the ZK coprocessor inside of Brevis. As I mentioned, like what ZK coprocessor does is that it allows you to generate a ZK proof of arbitrary computation on top of any historical on-chain data. And then you can use that data directly in your smart contract in a trust-free way. So using Brevis like ZK coprocessor is actually quite simple. The first step is you want to specify what type of data or what type of historical data you want to use as your input in your business logic. The second is that you want to specify what is the computation logic you want to run on top of these data. And finally, you write a smart contract to receive the callback from this off-chain computing infrastructure to essentially see, okay, now this is like the result of the computation. I can use that directly without trusting any third party because I know there's a ZK proof attached to it. So, to put it more concretely, like, for the first step, what type of data you can access? You can access literally anything, like, you can access that exists on blockchain, including storage state. These are essentially kind of variable values, who holds how much token, what is like the oracle value of some things in the past, or what is like the amount of liquidity stored in certain pools. All these things are included in the kind of a storage state part. And then there are receipts, which are events. Like these are the things that are related to user interaction mostly, right? Like, if a user made a swap on Uniswap, there will be the swap event emitted, and you can actually prove and use that data that, to do certain type of computation, such as transaction volume, such as volatility, and all of that. And then there's transactions, right? So the transaction basically include all the data involving the life cycle of the transaction, whether this is successful or not, who sent this transaction, so on and so forth. In many cases, transaction receipt and the transaction itself are used in tandem to generate some very interesting insights, about the blockchain. And of course, you have access to things like account nonce, like, chain state and blocking information as well. So we support any EVM chain, like practically speaking, these are the listed some examples. But any type of EVM chains, like we support them, very well. This is kind of a very, very simple code snippet where you can essentially add, a bunch of receipts using our SDK and API to say, okay, these are the data, or these are the type of data, or essentially the schema of data you are interested in your, kind of a business logic to process. And this is like kind of adding the swap event for Uniswap, right? So very concretely. So, for this part, you can also both use Go or JavaScript as an SDK to do this. And, after you specify what type of data and what kind of things you want to do, with Brevis, the second step is you want to specify what is the business logic, or what is kind of the actual computation you want to run, right? So, we provide a data stream API, like, you can imagine like this list of data you gather in the first step will be formatted in a data stream, and you can, use primitives such as map, reduce, filter, group by, sort, zip, and you can, plug in different functions in these primitives to process this data to get things like, simple things like sum, volatility, what is like the average, and all these stuff. But it can do a lot more than that, like by using these kind of primitives provided. You can even like figure out what is the LP's fee distribution, or what is the fee accumulated to a certain LP position versus the entire LP group in this pool. You can do something like this too with this type of combination API and logic. And in this very, very simple example here, what you're doing is essentially kind of just getting the sum of the swap event, which give you like the trading volume of particular user, right? So, and then finally, after the computation is done, you can write a callback function based on a standard callback interface to essentially receive the result on chain after the coprocessing is done, and then kind of execute the corresponding event or business logic for you, right? In the Uniswap hook context, you may have a before swap hook contract that has this kind of a interface or callback function where you can essentially write a user's VIP status or trader's VIP status based on the trading volume of this user, and then kind of after that, the next time the user come and do the swap, there will be a lookup to this kind of VIP table essentially, and then the user will get the corresponding fee discount. So like this is the process to essentially kind of build a full life cycle of Uniswap hook, and this hook can be a receiver or can be a callback handler of the off-chain coprocessing request. So if you want to build the same thing, like we talked about, like the trading volume thing with with Brevis, you basically have this kind of a function to get trading volume and call out to Brevis after the Brevis coprocessing is done. There will be a callback function to process the trading volume data, and it will be recorded in a hook contract, and then kind of get a process and then get effective for user to use in the future. So building the same logic and same business logic here is drastically lower cost comparing to directly do it on chain. And the latency is also very minimal, and the cost is also very minimal. So there are many different kind of use cases for Brevis, like data-driven DeFi is definitely a very, very big class. Uniswap hook is a big example for that, but there are many other kind of a modular DeFi DEXs like popping up, these days, like in the lending space, in the aggregator space, like in the intent space as well. Speaking of intent, like there are a lot of consumer application you can do with Brevis to do user experience personalization. That right now, if you look at all the Web3 apps, like every application is treating every user exactly the same, without actually considering what is their historical behavior in the application and in all side of applications as well. But like using Brevis, you can generate proof of user interaction, with application or with related applications, and then kind of use that profile to guide the user differently in the smart contract level directly without any trust assumptions. So these are the things that can be possible using Brevis. And then you can also do things like create very, very interesting things like intent automation. Right now, intent frameworks are all based on a single kind of execution, where you do one strike execution and you want to execute a certain kind of intent and they execute a certain swap at this moment, and you do it right now. But with Brevis, what you can do is that you can actually say that, okay, here is a pre-configured like a triggering condition, and only if that particular condition is met, I will actually do this kind of execution. And the Brevis can essentially generate a ZK proof for the intent automation framework to show on chain that, okay, this type of predefined condition, such as like the price of a certain asset reaches a certain level, is actually met. So you can generate you can build this type of trust-free intent automation frameworks. There are so many others like, things like MEV related infrastructure oracles that can be built, and the capacity can be extended with Brevis as well. So, these are some of the examples, but now, very concretely, what type of hook ideas you can build? Well, some examples that we listed out here as just like samples. One is the trading volume thing that we just talked about, and the second is that you can use, volatility-based pricing to essentially minimize the loss versus rebalancing, kind of loss. So that if the market volatility becomes high, then you essentially kind of have a dynamic fee module that can compute can generate or configure a higher pool fee, so that the LP's interest is more protected. And you can also do retrospective mining reward based on fee generated in each of the LP positions. Right now, if you look at all the trading kind of farming reward protocols, they are based on the time length of farming of the LP deposit. But what you can actually do here is to evaluate each of the LP's contribution to the protocol by evaluating on a kind of periodical basis what is the actual fee contributed by the LP to the protocol versus all the other LP's contribution, then reward the LP who actually is smart and can contribute the most of the fee to the protocol, and to kind of build new type of farming reward mechanisms here. There are many other criteria and things you can actually consider in this, but this is just kind of a sample example and an idea. And you can also, of course, do things like token holding based fee discount. You can compute what is the time-weighted average of a protocol token using Brevis, and then record that in the hook contract and activate the corresponding fee discount if the user want to buy the protocol token. Like if you want to kind of just like have a governance token holder to be able to actually easily acquire more governance token without actually paying a high amount of fee. You can also like do things like IDO or free trades based on on-chain OG status based on their kind of protocol and dApp usage to say, okay, if you are already a very, very heavy user of this particular application, then if you want to kind of trade this token, you don't actually need to pay any fee, right? So and also like you can build new things like user acquisition through on-chain user profiling to essentially generate a ZK proof showing that this user is already a big trader or holder of a certain token in other certain similar protocols, and then say, okay, if you are already a big trader somewhere else, you can get some benefits for trading in this new venue. You essentially kind of have this type of airline, a lot of airline have this, like, you can migrate your membership reward from one airline to another, like kind of you can migrate your membership status to one airline to another, as long as you keep kind of hitting certain goals in this new venue of trades. And there are so many different ideas around this, but the key thing here is that you can actually generate a lot of data insight based on both the overall protocols behavior, like the price volatility, like the other protocols like behavior, and on an individual user level, what is kind of users' behavior to the protocol, and you can individualize and personalize the user experience, using hooks and Brevis together. So these are just some quick examples, happy to chat more, and we are very much available in our social channels and in our Discord and also like Telegram group. If you have any question regarding using Brevis, just like hit up the ping us there, and we'll be more than happy to help. With that, I will first pause here and see if there's any questions that I can answer immediately, and then I'll hand over this to Junda for more of the SDK introduction.
I have a question.
Yeah, I think we have a couple of questions in the chat.
Yeah. Oh yeah, I can just like maybe I can just go down the list. So Matthew Alexander asked a question that what is the difference between ZK coprocessor and ZK VM? Well, I think from kind of a broad stroke, ZK coprocessor and ZK VM are both off-chain verifiable computing attacks. So basically, they all do some off-chain computing and generate ZK proof that you can use directly on-chain in the smart contract. Now, the difference between ZK coprocessor and ZK VM is like in terms of whether there's it's a trade-off between specialization and kind of a performance. So with ZK coprocessor, with like what we just kind of introduced now, it is very much tailored towards the use case where you want to access certain historical data on chain and then do computation on top of that. So the performance of ZK coprocessors, in that particular case, is going to be much, much higher than any ZK VMs available today. But of course, what ZK VM can do is it's give you a very, very generalized computing environment where you can essentially write high-level languages like Rust. and then do the computation result. But it is definitely beneficial if you want to do something other than like kind of the on-chain historical data access and computation use case. And for more complete view, I actually like recently got asked a lot about this particular question. So I actually wrote a long thread about this, to understand like what is the specialized versus generalized ZK, which one is actually going to be the future. So I'm just going to post this here for your reference as well. So, Ahmed asked a question, also wondering about the cost of ZKML proof and the ZKVM proof. Right. So, that really depends on like the kind of a proof system that you use. For certain proof systems, the proof size will also still be constant. And, for most of the cases, what we see instead of, for whatever things that it can be used in the smart contract, finally, people try to do recursions based on, based on whatever like the kind of people try to basically kind of recursion and compress the proof finally down to growth 16, so it can be verified on chain directly with constant size and very limited, very small amount of like kind of a gas cost. So this is like generally how people are approaching it. For example, for ZK coprocessor that we built, there are intermediary proofs, like there are smaller proofs generated for each of the data points, and then there is also proof generated for the computation, and then we kind of stitch them together and finally compress them down all to the a growth 16 proof on the BN254 curve, so that it can be verified efficiently as well. So there's another question mentioning, would you say the main benefit of Brevis is that it can handle computation offline and submit a ZK proof ahead of time, so that when it's needed during a transaction, we can access the pre-computed data with low latency. Also, how can we get access to this pre-computed data in the smart contract? Do we have to use an oracle like Chainlink, or does Brevis has its own oracle? So this is a great question, right? So this comes back to the kind of a design pattern question we talked about. So the general design pattern here is that you have some on-chain contract, want to do some computation and use that at a later stage. So this is where there will be a kind of a smart contract called for from this smart contract saying that, hey, I want to do some computation, like maybe I want to get some like trading volume for this particular user. Now what happens is that the off-chain computing part will see this particular call and then kind of trigger and get it invoked to actually do the computation and generate the proof. After the proof is generated, then the proof and also the computation result will be posted back to a Brevis smart contract, like Junda is showing this graph right here. And this Brevis contract will then call a callback function in your application smart contract. Let's say in this particular case, we just calculated the trading volume, and finally the Brevis contract will do the proof verification for you. And when the proof this particular function actually calls back to your business logic, you can trust that whatever contained in the callback is actually already proved. So this is like how you can access the data. So in a way, it is kind of a specialized oracle in the sense that it posts back to the blockchain with a proof, and then the data get posted to your smart contract, and then you kind of you use the data just like how you use the result, just like how you would use an oracle, for example. But it is not through Chainlink, but through kind of a Brevis's own infrastructure.
Yeah, maybe we go over this more concrete examples with some actual code.
So let me just kind of try to also, I think a very concrete example from Junda would be super helpful. just one. Let me kind of go through some of the proposals.
Yeah. No delivery. No worries.
Yeah, so like I think there's also a very important question, like could you please say more about latency? How much does of it processing time versus like uploading to the blockchain? Would it be realistic to say optimize trading strategy in real time? So the latency of using off-chain computing, and especially in ZK context, is something to consider for sure. So for example, like generating a large amount of proof, like maybe 1,000 transactions to generate the trading volume of 1,000 transactions, for example, with like 8 cards, like 8 GPU cards, will cost you about 100 seconds. Right now, in the next generation, it will be much faster, but right now it costs you about 100 seconds to generate that. So that's something to take into consideration. But the key thing I want to note here is that it is a matter of feasibility, right? So like even if you want to do this directly on chain, there was no way to actually do this on chain because the latency is going to be much longer and the cost is going to be much higher. But yeah, so there are going to be some latency involved in this, and that varies depends on your kind of a workload and the workload and use case specifically.
Sorry.
Yeah, so like also very important question from like Key, that is like with Brevis data access service, how does one know that data was not faked, right? So this is like very important because the Brevis kind of entire proving stack proves the entire kind of computation process end to end, in the sense that it proves both the input data is actually correct and exists on blockchain. Like this transaction, if you want to do some computation based on a bunch of transaction data, right? So like it first need to prove that these transactions actually exist based on the block header available, right? So like a block header is essentially a summary of all the historical states in the blockchain. It's a hash of a hash of a hash of a hash, like to compress down to the block header, right? So like we can generate proof showing that okay, here is a block header available on the blockchain, and we can prove that all these data actually exist on the blockchain. So this is how we can ensure data integrity. That is because the entire proof is end-to-end safe. Yeah, so it also kind of correspondingly answered the question from Sid, that the historical data off-chain comes from somebody like Chainlink, because no, because like because like the data the data itself comes from the blockchain itself, and then you can get the data anywhere you want. Like if you want to prove certain data and then prove some computation on top of it, you can get the data anywhere you want. You can get the data from Alchemy, you can get it from Doom, but once you input it into Brevis, there's no way that you can actually fake the data, because like the proving process include that the attestation of the data validity itself. Yes, Matthew, you will definitely receive the slide. I will kind of send out the slide link, afterwards. And yeah, so this is like not really related to FHE or homomorphic encryption here, because like this is the FHE and the homomorphic encryption is more related to the privacy use case. Even though we use ZK here, it's more about the scalability rather than the privacy property here. Cool. I think I just like went through the whole list of questions, but I will let Junda to take over here.
Okay. Yeah. Yeah. I will just start from this kind of end-to-end workflow for Brevis. As a developer, I hope after Mo's talk, you'll be really excited to integrate with Brevis SDK and really to enable some fundamentally new paradigm or use cases in your DApp, right? With the power of ZK-proved historical on-chain data. And at the same time, I will try to also address in more details, concretely, some of the questions. For example, the first step, you as a developer, you know where to get the data you're interested in, right? It can come from anywhere, like Mo mentioned. It doesn't matter, yeah. And we don't worry about, is it genuine or faked, because whenever you submit the data together with your in-app proof to Brevis, the Brevis prover will make sure it matches the block. You say, okay, in this block number 123, I found this transaction. Brevis service will not just blindly believe that, right? It actually has to go check, does this transaction hash all the way to the transaction try root, and then together with all the other receipt root and state root together, hash into the block header, right? So that's kind of the Mo mentioned, the end-to-end data integrity check. So from this part, the validity or the integrity of the data itself is guaranteed. And then the second part is the logic, like the computation, like you do the sum over trading volume inside your own app circuit, right? That's guaranteed also by the ZK proof underneath. And in addition to the native Go SDK, we also provide a TypeScript module now. It actually will interact with the prover service, and later on, after the proof is your in-app proof. So basically, I want to try to emphasize there is actually two layers of the proof, right? When you say, oh, I want to compute a trading volume sum, then inside your own application, the off-chain component, the ZK circuit part, it will generate a proof for this part of computation. But then, like many people ask, how do we know the input of the data is right? Well, that's where the Brevis proof comes in together. So basically, in the end, it will actually be aggregated proof. The Brevis will combine both, right? The underlying data integrity proof plus the app-specific, say, sum, the calculated sum is correct. Right? And from the API perspective, once you start the, this here actually use the TypeScript example. It's equivalent in Go, just make it a little bit more, there is one more round of RPC communication because the actual proving server is run as a separate service, right? It could be anywhere, but during development phase, it's more likely to run on the same machine. And then within your code, you will add the data you're interested in, right? For example, we still go with the Uniswap trading volume example. The data or the data points you're interested in will be in the receipt, because when they emit the swap event, right, the log, in Ethereum EVM term, it's included in the receipt, transaction receipt. And in the receipt, you will specify, hey, here is the event, and here is the field. Like, for example, in swap event, the first unindexed field is the amount 0, basically the token 0 swap amount. And this is the, as a app developer, this is the data you will basically, no one else will know what are the data you're interested in. And you will collect this data, like Mo mentioned, you can query it from any RPCs or some of the off-chain indexers that are already available. And the best thing is you don't need to trust that, because if it's some of the fake data, it will fail at Brevis prover later, because Brevis prover will say, hey, I don't see this piece of data in the block you claim. Right? And the next step is you still have to write something, right? As an off-chain, the ZK circuit, but we have done tremendous work to wrap up the underlying, the ZK complexity and expose a simple and intuitive API. In your code, you just need to tell us what's the maximum number of receipts. Like in this example, say you say at most I want to handle 100 or like 1,000 receipts or event logs in concrete term, the swap events. Why do we need this, right? I think someone asked about the latency. It's always the trade-off. The more potential receipts you want to handle, we need to spend more hardware resource to generate a proof, right? If you know in your use case, the number, say, will never go more than 100, we can actually have a much more efficient underlying infrastructure to support the proof to give you much better latency. If you say, oh, my use case always require 5,000 receipts, right? Then it's another trade-off between how many GPU instance we spin up for the proof. Then it eventually will come down to who is willing to pay for this additional resource to get faster proof. And inside the app circuit developer right, you can tell from here, right? So I think Mo also mentioned we recognize it's more for data analytic use cases. We actually introduce some MapReduce-like APIs. Like here in this example, to compute the sum, the total volume of the transaction. As a developer, you literally just call SDK.sum, right? So this kind of is how we see the use cases, what we want to like make the developers' life easier. Instead of you of course you can write your own loop, but on the other side you have to handle all this underlying ZK complexity. But with exposing high-level API like sum and all the other quite common data analytic functions, as a developer, inside your circuit code, it's just like this. You go over the receipt and make sure the first part it does absolute, because if you check the actual swap event, if it swap out, I think that because essentially a delta amount, right? So basically the amount 0 could be negative. And when you do the sum over trading volume, of course, you don't want the negative number mess up with your positive trading volume. So you want, first step, the volume actually goes through each receipt and make sure the swap amount, if it's negative, it will become positive. And then in the last line of this slide, you literally just do SDK.sum, and you get the total volume. And all the underlying complexity is already handled by the Brevis SDK. And in the end, you need to tell all the downstream components what you're expecting to generate as the final computation result. Right here, there is more example than needed. If we only care about the trading volume example, you only need the sum volume and the user address, right? And all the other, like the sort and the minimal, the smallest block number is more like in our example, we want to show how developers can expose other kind of data. Now come down to the on-chain contract. I remember someone asked, how do they really use this data, right? In the earlier slide, you should see after all the proof is generated, it will be submitted into the Brevis core contract to make sure the proof actually is valid. Right? That's the beauty of ZK thing, right? In the end, it will be a very succinct proof submitted on-chain, and the on-chain Brevis core contract will do all the verification to make sure, yes, it is legit, it is passed all the checks, and then this is the result that later it will call the developer contract. So in your smart contract, you only need to implement a single function called handle proof result, which is the result your off-chain circuit code just output. So basically in this example, in the previous slide, you will first output bytes 32 and then all the uint depends on how many bytes you actually need. And then the final is the user address is the 20 bytes, right? And here, similarly, when Brevis contract calls the developer contract handle proof result, this result has already been vetted by the core contract, goes through the ZK proof verification, and then you can just decode, because limited by the Solidity interface, we cannot really pass arbitrary struct or something. So we just have to give you a byte call data, right? And then within your smart contract, within your handle proof result, it's up to the developer to decide whatever way you want to decode your output. Right? Here you can see after the decode, I will actually show the decode code in the next slide. And this should match your circuit output because it is identical data. So let's say after go through some of the receipt, your circuit generate the result. It will be passed over to here in the circuit output. And within your smart contract, here, of course, it depends on whatever result is generated from your circuit, right? We just give you here a simple example to say you just use the byte array index to say, oh, first is 32 bytes, and then the rest are followed. This is it. So that's already give you a full end-to-end flow of how do you, if you want to really integrate with Brevis SDK, write some Go code in the to generate the circuit, and then here inside your smart contract, you just need to implement the handle proof result, decode the result, and use it whatever way you like. That here in this simple example, you already have the sum of the volume. You could just maintain a map, say, oh, if the volume is bigger than some number, assigned to a different status, right? And another minor thing for Uniswap V4, I think if you want to enable dynamic exchange, swap fees, there is an additional flag you need to set. So basically, that to tell the Uniswap core contract that, hey, when you do swap, the swap fee could be different because your hook will tell the core contract what the fee is, right? Using the update dynamic swap fee function. Yeah, I think the high level idea I want to make sure everyone gets is, as a developer, you still write your smart contract, in Solidity. It runs on chain, and you only need to implement a simple function called handle proof result. And all the underlying heavy lifting is already handled by the Brevis, both the Brevis SDK and Brevis proving service plus the Brevis core contract. Right? As a developer, you need to make sure it's the Brevis core contract calls your handle proof result, and do with the circuit output result whatever way you see fit. Yeah, that's it. Yeah, I see the last question is that, can we choose the app prover runs on your local machine? Yes, that's where if you see the where is it? Here, right? This slide. The prover service, right? The app specific prover is run by the developer. Of course, you are free to offload this to some other what they call prover network. It's up to you, right? There's never a strict restriction where exactly you run, but it's developer's responsibility. But on the other side, as I mentioned, all the proof for the integrity of the data, like literally go over the entire history to check, oh, the receipt or transaction, whatever storage slot matches, hashes all the way up to the block header, block hash. That's super expensive, and that's maintained by Brevis because it's also as a common utility, right? It's a common good service. We maintain that for each chain, and when the developer says two different developers generate their own proof, they could use different block or even use the same block. When they come to the Brevis core service, the Brevis prover is already know, oh, these blocks, what are the data I can take a look, right? So when the developer say I'm using these receipts from these block numbers, Brevis prover is already actually has that. Let's see. Is there any other question? Let's see. You need to know zero Rust. That's a good thing. And our hope is, if you check, I hope I made it clear. When you write your ZK circuit, you literally can have zero knowledge of the ZK space, right? You don't really need to understand all this underlying said growth 16 curves, whatever fields, right? Those things are already hidden inside the SDK. If you are interested, of course, you're more than welcome to read the internal code inside the Brevis SDK. Everything is public, open source. But as a developer, if you say, I want to quickly start, go check our example folder. There are tons of get started examples, and those are actual real examples, and not some like fake hello world doesn't do anything meaningful. Like in the examples folder, we show you how you can prove an account age and how you can prove like the trading volume is obvious, right? And all the other fancy, you can do more complicated off-chain computation over the data. Is there any instance in which how do you define wrong data? The beauty of blockchain is every piece of data, no matter where it is, right, has to be able to be verified. So say you tell us, oh, this block number, my ERC20 token balance is this. No, we don't need to believe that, right? That's all I'm trying to emphasize earlier. That's all the heavy lifting done inside the Brevis prover. We actually had to run a pretty heavy infrastructure just to do that. If you think about it, every transaction, every receipt, and every state change, it will be included in the Ethereum block trie, right? So basically, there are many. I think it's already more than 20 fields now. And then say for the transaction tree or trie, it's a Merkle tree, and you literally start from the leaf and hashing all the way to the root, and you say, okay, this is the transaction tree trie root, and then you combine together with the other, say, receipt trie. So there's no if there is a data that doesn't pass the validation, it just failed the Brevis prover. That's basically you are talking, that has nothing to do with ZK, right? So basically, okay, you're basically talking about the chain reorg. Is that the chain reorg is, I wouldn't think,
So I think it's kind of an orthogonal question. Like, if there's it really depends on when you want to generate the proof, right? So like, our recommendation here is that, you only generate proof regarding blocks that are finalized. If you want to use this for the same chain use case, but there are some, other use cases that it doesn't really care about forks, like, in the MEV context, they're okay with generating proofs more opportunistically. But yeah, so like that's kind of like the recommended way of doing this. One other related question to this is like, let's say you want to do some sort of a computation based on a group of data, and there's some sort of like a filtering logic about this data, right? So like, let's say if I want to do some computation based on this user trait, or like, I want to kind of make sure that all the things that is like there, like if you want to do, say, for example, the most simple way to kind of explain this is that if you want to prove a user never interacted with Uniswap, how do you want to do, how do you do that? Well, it's for these type of computation, it's actually very hard to do in ZK or in pure ZK, right? So like, it's a, for example, if you want to prove that a account never interacted with Uniswap, it means you need to prove the entire history of the blockchain to show that, okay, among all the blockchain transactions, there's just no transaction that this user ever interacted with Uniswap, right? So, how you, this is like infeasible to do, basically, if you want to kind of prove the entire history of the blockchain for every single transaction. So how do you want to kind of solve this is that we have something called Brevis coaching, which I will also send to the group now. Is what it does is that it allows you to do this kind of optimistic co-processing with ZK fraud proof that we're going to release soon. So what it does is that you can say, okay, a proof of stake system or optimistic proposer will propose and say, okay, look, I propose and claim that there's no transaction between this user to and Uniswap. And only when you want to challenge it, you actually incur a ZK computation. For example, to challenge this type of non-existence, you can just generate a single proof of existence of a single transaction to say, hey, look, I can prove there is indeed a transaction between this user and the Uniswap, and the challenge will be successful. So this type of kind of a additional mechanism will be available in Brevis to handle cases like proof of non-existence and proof of completeness as well. Awesome.
Awesome.
Well,
think we have one.
just to answer Matthew's last question
Yeah.
here, like, can we assume that like this particular repo, in the example, the circuit.go is the verifier? Well, the circuit.go is the business logic, right? So like, the business logic basically specify what is kind of the balance of this particular user, like how to kind of calculate that. The verifier actually, like, the prover lives off chain, and based on this circuit, a prover will be able to, essentially kind of a circuit will actually be based on this SDK file, the Go file. A circuit will eventually be compiled and generated that can be run in the off-chain environment to generate the proof, and also a corresponding verifier contract will be generated as well. Like, the verifier contract or verifier, the verifier contract will be generated that can be deployed on the blockchain. So in this case, the blockchain smart contract becomes a verifier. Yes, like that's precisely. That's essentially the source code to specify the business logic that can be used to automatically generate the prover and verifier.
The verifier always lives on chain as a smart contract, because I'm not sure how we address this question. I think there are some fundamental, maybe some concept. When we say verifier, right? So it has to live on chain. Otherwise, what's the root of your trust, right? The verifier lives on chain, runs in Solidity EVM, and say, yes, this proof is correct. Then we are confident to pass the result to the developer's contract, right? I think the circuit you write, as Mo mentioned, is your business log. You as a developer, you know what data and what calculation or computation you need, and you in your circuit you generate, you will write output some data, right? And then after all the heavy work is done by the Brevis infrastructure, it will be sent on chain to Brevis core contract, which does the verification work. Basically, that contract verify the ZK proof of pass, and then it passed on to the developer contract called the handle proof result. I hope that's clear enough. I think the verifier can, if you say I run the verifier off chain on my own machine, who can trust that, right? So I think the verifier always runs on chain as a smart contract.
Awesome.
Awesome.
Yeah. Thank you guys. Thank you, Mo and Jinder, for like having these amazing workshops, like showing us what Brevis can do and like showing us what Brevis can do with Uniswap books. And yeah, thank you for answering the questions also. Also for the people
thank you all for
in the chat.
you asking all the great questions.
Yeah. I put a workshop feedback in the chat, so if you guys could fill that out, we would love to learn how to make ourselves better. And yeah, thank you, Mo and Jinder. Thank you, amazing session. Yeah, thank you everybody for joining.
Yeah, we'll be available in our chats and stuff, and you can always reach out to Manu and the Atrium team if you have questions. Like, we're happy to kind of answer them, and we can pull groups and stuff like that. So
yeah. Also, we do have a Brevis channel on Discord, so if you guys have like questions,
yes, we do.
Yeah. Please do post questions there also. Yeah.
Yes.
Awesome.
Thanks for reminding me that.
Yeah.
All
Awesome.
right. Thank you, guys.
Bye, guys. Thank you.
Nice day, night, or evening, afternoon, morning. Bye.